For many years, the petrol engine has been the powerhouse of the majority of passenger cars and a high proportion of the smaller commercial vehicles. Diesel engines, on the other hand, had the reputation of being noisy, smelly, heavy and sluggish, not at all pleasant to live with. Their use was limited mainly to heavy plant machinery, farm vehicles and large trucks. But things are changing. Passenger cars and small vans are now being powered by a new generation of smaller capacity diesel engines. The lower running costs and durability of diesel, or more correctly, compression ignition engines, are particularly attractive to fleet users, and there's a growing demand among private motorists, particularly because fuel savings can be considerable. Austin Rover, recognizing this, has developed a new high-speed diesel engine in conjunction with Perkins, a manufacturer whose experience of diesel engine design is second to none. This new engine, based on the M series, will be known as the MDI. One of the most significant differences with this engine is that direct rather than indirect injection is used, unusual for an engine of this size. This program, the first of two on diesel, compares the operation of the diesel engine to the petrol engine. We'll then take a closer look at the fuel system and its servicing requirements. In construction, the diesel engine isn't greatly different from its petrol-burning counterpart. Its fuel injection system is generally more sophisticated than the fuel systems used on the majority of petrol engines. The compression ratios used are very much higher, and the engine speed is governed to lower levels. Flywheels tend to be heavier to smooth out torque fluctuations, enhancing the ability to pull strongly at slow speeds. But before we look more closely at the diesel engine, let's recap on the basic operation of the conventional carburetor-controlled petrol engine. The fuel and ignition systems on a petrol engine incorporate 5 main components: a fuel pump to deliver fuel to the carburetor, a carburetor to mix the fuel with the air, an ignition coil to convert low-tension voltage to high-tension voltage, and a distributor to distribute the high-tension voltage to the spark plugs. Most engines, both petrol and diesel, operate on a 4-stroke or Otto cycle, but there are significant differences in the combustion process of each type of engine. We'll look first at the 4-stroke cycle of a petrol engine. The first stroke in the cycle is termed the induction stroke. The fuel-air mixture is drawn into the cylinder via a carburetor as the piston descends in the cylinder bore. Having filled the cylinder, the piston moves upwards on the compression stroke, compressing the mixture to a ratio of approximately 9:1. The compression ratio is determined by the relationship between the volume of air and fuel mixture with the piston at bottom dead center to that when the piston reaches top dead center. Just before the piston reaches the top of its stroke, the ignition system supplies a high-voltage spark through the spark plug electrodes to ignite the mixture in the combustion chamber, forcing the piston downwards on the power stroke. The piston then rises on the exhaust stroke to force the spent gases out of the cylinder. If we now consider the diesel engine, we see that there are several fundamental differences. There's no distributor or spark plugs, ignition coil, carburetor, or conventional fuel pump. The components used on a diesel engine are a low-pressure fuel lift pump to draw fuel from the tank, a fuel filter, a high-pressure fuel injection pump, and a fuel injector for each cylinder. Unlike the petrol engine, only air is drawn into the cylinder on the induction stroke, and to ensure the air heats sufficiently to provide combustion, higher compression ratios are used. The compression ratio is approximately 18:1, around twice that of petrol engines. As air is compressed, its temperature increases. If you've ever inflated a bicycle tyre with a handheld pump, you'll have noticed how warm the end of the pump becomes. This is a simple demonstration of how the temperature of air increases when it's compressed. Just before the end of the compression stroke, atomized fuel is injected into the combustion chamber at high pressure. The temperature of the air inside the cylinder at this stage is much higher than the flash point of the fuel, causing spontaneous combustion and forcing the piston down on the power stroke. Then, like the petrol engine, the spent gases are discharged on the exhaust stroke. The major attraction of the diesel engine is its fuel economy. Due to its superior thermal efficiency, a diesel engine uses less fuel than a petrol engine for the same engine load. To illustrate how this is achieved, we'll look at the heat losses which occur in an engine. First, a petrol engine. 33% of the heat produced is lost to the cooling system, 10% to friction, and 33% to the exhaust system. This leaves about a 24% efficiency available at the flywheel for useful work. Now, when we look at the diesel engine, the comparative heat losses are 31% to the cooling system, 11% to friction, and a considerable saving in heat loss to the exhaust system of only 24%. In this case, the usable effort left is approximately 34%. It therefore follows that if the thermal efficiency of an engine is improved, it will burn less fuel for a given power output and hence be more economical to run. The fuel injection equipment fitted to diesel engines is manufactured to extremely fine limits, enabling precise metering of fuel over the complete speed range. This degree of control is not usually found on the majority of petrol engines and is another important factor in the diesel achieving better fuel economy. Additionally, provided that contaminated fuel is not used and that fuel filters are renewed during servicing, the fuel injection equipment requires less servicing than the fuel system components fitted to most petrol engines. So vehicles tend to be off the road for less time, an extremely important factor to both the fleet user and the private motorist. One characteristic of diesel engines is the familiar diesel knock. The knock occurs because of the delay period between fuel being injected and complete combustion taking place. When fuel is injected, it causes a small temperature drop in the cylinder, and burning starts on the surface of the fuel droplets only. As the fuel continues to burn, both the temperature and the pressure within the cylinder increase until the remaining fuel ignites. This causes a huge pressure rise, which in turn creates the knock. To ensure the combustion knock is kept to a minimum, the injection pump timing and injector settings must be correct. For instance, if an injector setting is low and opens prematurely, combustion in that cylinder will commence too early, increasing the knock. There are two types of injection system used in diesel engines: indirect injection and direct injection. Let's compare the two systems. Indirect injection operates at lower peak pressures and is able to control the combustion process better than was the case for direct injection. It therefore tended to be quieter at idle, whilst also being able to operate at higher speed. Although it's less efficient than direct injection, its quietness and ability to rev highly often made it first choice for car applications. An indirect injection engine, or IDI engine as it's known, incorporates a separate pre-chamber within the cylinder head. On the compression stroke, air is forced into the pre-chamber, promoting a swirling motion. Fuel is then injected via a pintle or single spray type injector to start the combustion process. As combustion progresses, the burning air-fuel mixture is forced out of the pre-chamber at high velocity to continue combustion within the cylinder bore on the power stroke. The Austin Rover MDI engine is a 2-litre high-speed direct injection diesel engine. Direct injection, or DI engines, are more efficient, but they operate at higher peak pressures, so control of the combustion process over a wide speed range used to be more difficult. In the past, they tended to be noisier at idle and were previously less flexible than their indirect injection counterparts. However, with the MDI engine, the control of the combustion process is such that the knock and the ability to operate at higher speeds are now comparable to indirect injection systems, whilst enjoying significantly lower levels of fuel consumption. The air movement required for good combustion is obtained over the induction and compression strokes by careful positioning and shaping of the induction ports and the cavity in the piston crown. When the piston descends, it draws air into the cylinder in a swirling motion. As the piston rises on the compression stroke, the swirling motion increases in speed and is finally concentrated into the piston cavity. Fuel is then injected directly into the piston cavity, the hottest part in the cylinder, through a multi-hole injector to give super efficient mixing of the fuel and air. Further mixing continues as burning progresses until combustion is completed. A direct injection system operates at high peak pressures and temperatures, therefore achieving high thermal efficiency and lowest specific fuel consumption. When starting any diesel engine from cold, it's normal practice for the throttle to be held open, thus allowing the maximum amount of fuel into the cylinder. Due to the low ambient air temperature during winter, IDI diesel engines require help when starting from cold. Electrical starting aids known as glow plugs warm the air in the pre-chamber. Depending on individual engines, they operate for a period of time before and during starting. Glow plugs are also fitted to the Austin Rover MDI engine. These give it faultless starting characteristics, a feature the modern motorist has grown to expect. The type of glow plug fitted reaches a temperature of 850 degrees Celsius within 2 seconds and allows near instant starting, even at temperatures well below freezing. Now, one final point before we move on. Because diesel engines produce very little intake manifold depression during operation, there's a vacuum pump on the cam cover which supplies vacuum to the braking system servo. So far, we've covered engine operating principles and looked at the main differences between petrol and diesel variants. So, stop the tape and answer the series of questions in section 1 of your questionnaire booklet. When you're ready, restart the tape and resume the programme. In this second section, we'll look at the diesel fuel system in some detail, together with its servicing requirements. It must be emphasized that when working on the fuel system, all components must be absolutely clean. Even the smallest particle of grit could cause irreparable damage to a fuel injection pump. Under no circumstances must water be allowed to enter the fuel injection system. To prevent this occurring, fuel filters include drain cocks, and maintenance procedures specify regular checks for the presence of water. These checks are of the utmost importance. They're usually carried out at weekly intervals and must not be overlooked. The fuel lift pump, driven from an eccentric cam on the camshaft, supplies fuel to the fuel injection pump via the fuel filter. Air should never be allowed to enter the fuel system, but if it does, there's a priming lever on the pump housing which allows the system to be bled. A metal gauze filter within the pump body must be removed and cleaned every 48,000 miles. The fuel filter is a disposable canister which must be renewed at least every 12,000 miles. This is extremely important to ensure that debris doesn't get into the injection pump. After changing the filter, release the bleed screw sufficiently for air to escape and operate the fuel lift pump priming lever until bubble-free fuel emerges. Then tighten the bleed screw and wipe the filter clean. A word of warning. Fuel can emerge at high speed from the bleed screw, so care must be taken to ensure personal safety and that no unnecessary spillage occurs. The Bosch EPVE distributor type injection pump used on the MDI engine operates on 3 fuel pressures: a low or inlet pressure, an intermediate or transfer pressure where an internal pump raises the fuel pressure prior to its transfer, to the high pressure system where the fuel is delivered to the injectors. The high-pressure system operates at 500 to 600 bars, where 1 bar is equal to 14.7 pounds per square inch. This means that fuel pressure in the high-pressure system can reach over 8,000 pounds per square inch. Fuel at this pressure can easily penetrate the skin, so great care must be taken when testing the opening pressure of the injectors. A mechanical governor driven by the injection pump drive shaft prevents the engine over-revving by progressively reducing the amount of fuel delivery beyond a preset limit. This ensures that the engine operates within its most safe and efficient limits. The injection pump fitted to this engine is a self-priming type. This makes it very much easier to bleed the high-pressure system than on the older generation of injection pumps, where it was quite common for there to be 2 or perhaps 3 bleed screws fitted to the pump. On this injection pump, there are no bleed screws, and bleeding the high-pressure system is simplicity itself. With the fuel filter fully purged of air, loosen the inlet union banjo bolt and operate the fuel lift pump priming lever until bubble-free fuel emerges, remembering to use a cloth to soak up the fuel. Then retighten the bolt. Loosen the injector unions and depress the accelerator fully, then operate the starter motor and tighten each union nut as fuel emerges. Continue to operate the starter until the engine runs unaided. The injection pump doesn't require routine servicing, but if it needs overhauling, it must be removed from the vehicle and taken to a specialist repairer who has the required test equipment and necessary expertise. However, there are 2 adjustments that may need to be made when servicing the engine. First, the engine idle speed, and second, the push rod for the cold start fast idle solenoid. To measure the idle speed of a diesel engine, this type of tachometer can be used, which reacts to reflected light. To show this operation clearly, we've removed the front wheel. What you do is attach a piece of reflective tape to the crankshaft pulley and start the engine. Hold the tachometer with its light source pointing at the reflective tape. Then depress the button and a reading of the engine speed will be displayed on the dial. To adjust the idle speed, turn the screw nearest the cylinder head until the correct reading is achieved. The fast idle solenoid push rod may be adjusted if necessary. First, energize the solenoid by disconnecting it from the harness and substituting a constant live feed to the solenoid connector. Then, use a small spanner to set the fast idle to the correct speed. Each time you change the push rod length, you must open the throttle to permit the push rod to settle to its new position. This is because the solenoid isn't powerful enough to push the throttle lever on its own. It's merely fitted to hold the throttle lever in a preset position, achieved by moving the accelerator pedal. The solenoid is controlled by the temperature sender unit in the thermostat housing. At approximately 40 degrees Celsius, the solenoid will be de-energized, and the fast idle will revert to normal idle speed in one movement, rather than being progressively reduced as the engine warms up. Diesel engines are stopped by cutting off the fuel supply. When the master switch is turned off, the solenoid plunger cuts off the fuel supply to the high-pressure system. When the master switch is turned on, the fuel supply is reinstated. This solenoid replaces the stop cable used on many previous injection pumps and enables a key-operated stop-start similar to that used for petrol engines. Checking its operation is a two-man job, one to turn the master switch on the steering column on and off several times whilst you hold the solenoid body. You should feel movement as it operates. If necessary, the stop solenoid can be renewed. Whilst we're looking at the injection pump, a word of warning concerning the delivery valves fitted in the hydraulic head. When they close, they give a precise shut-off at the injector by reducing the high-pressure pipe fuel pressure extremely quickly. Always use 2 spanners to loosen and tighten the high-pressure pipe union nuts, or the delivery valve may become distorted, causing faulty operation. Under no circumstances should these unions be over-tightened. The pump is also fitted with a cold start unit. Its function is to advance the injection timing in excess of its normal level whilst the engine is cold. When a diesel engine starts from cold, the heat generated during the compression stroke will dissipate readily through the cold cylinder walls and cause a lag in the combustion process. By advancing the injection timing when the engine is cold, combustion will start sooner and compensate for this lag. When the engine is warm, this sensor on the cylinder head will operate the wax stat unit and cause the cold start unit to cease operation. The injection pump will then revert to its normal timing characteristics. The wax stat incorporated on the cold start unit may only be removed by experienced personnel at an injection pump service centre. One final point before we leave the injection pump. Never interfere with this screw here or remove the arrow-shaped spacer. It's used for locking the pump shaft during production and must not be used for any other purpose. If the spacer is removed, the screw will cause internal damage to the injection pump if the drive shaft is rotated. The injectors are of a multi-hole type and they spray atomized fuel directly into the piston crown. They're sealed to the cylinder head by a single copper washer, which must be renewed each time an injector is removed. A location ring is fitted for centralizing when the injectors are fitted to ensure even sealing on the copper washer. It's very important that the injector blow-off pressure and spray pattern are correct. An injector tester must be used for this purpose. Secure the injector to the tester with these pipes and operate the handle moderately quickly. Observe the spray pattern and make sure the fuel spray is well clear of your hands. On this injector there are 4 individual sprays. If the setting or blow-off pressure of 225 bars is incorrect or the spray pattern is not uniform, then the injector must be renewed. The glow plugs can also be tested, either on or off the engine. The glow plug tester is simple to use and shows the current drawn and how long it takes for the current to stabilize. To test the glow plugs on the engine, they must be isolated from each other by disconnecting all electrical wiring. Connect the black lead to the negative battery terminal and the red lead to its positive terminal. The yellow lead should be connected to the glow plug center pillar. Depress the test button and note the initial current drawn and the time taken for it to stabilize by observing these LEDs which illuminate at 5-second intervals. To enable the glow plug relay and timer control to be tested, the red lead must be connected to the live feed from the harness, leaving the other 2 connected as in the previous operation. Depress and hold the test button, turn on the master switch and note when the dial needle drops to 0. Use the LED timing scale to note the time taken. When testing a glow plug off the engine, push it into the clamp at the end of the tester, connect the yellow wire to the glow plug center pillar and depress the test button. Note the time taken for the current to stabilize and check that the glow plug element glows at the tip end first. As we said before, the glow plugs must be tested individually, but should a mistake occur, an overload switch on the tester will protect the test equipment and the vehicle wiring harness. The glow plugs are first checked at 24,000 miles and every 12,000 miles thereafter. Well, now you've come to the end of the section. Stop the tape and answer the series of questions in section 2 of your questionnaire booklet. When you're ready, restart the tape and resume the program. In the event of an engine, fuel system or air supply problem on the diesel engine, a clue to the cause can very often be indicated by the colour of exhaust smoke. There are 3 colours of exhaust smoke: blue, white and black. All smoke tests, especially that for black smoke, must be carried out with the engine at normal operating temperature. Blue smoke is usually caused by the burning of lubricating oil and indicates internal wear in the engine. This indication is exactly the same as on a petrol engine, and the same diagnostic procedures apply. White smoke is vaporized unburned fuel caused by insufficient heat within the cylinder. Another reason could be that the injection timing is retarded, meaning the fuel is being injected later in the combustion cycle. If so, the heat within the cylinder has passed its period of maximum intensity, so the fuel becomes vaporized but not burnt. Possible causes of white smoke are a partially blocked air cleaner, a faulty glow plug on a cold engine, or an injector fault when the engine is off-load. Black smoke is partly burned or unburned fuel and is the colour most associated with diesel engines, probably because it's most easily seen. The components most often condemned and least likely to be the cause of black smoke are the fuel injection pump or the injectors. First, check the air cleaner element for a blockage which restricts the air supply. This means that there's not enough air available to burn all the fuel injected. Another cause may be the valve clearances. Valves with excessive clearance open later and close sooner, again tending to restrict the air supply. The next step is to remove and check the injectors for faulty operation. Whilst removed, a cylinder compression test may be carried out, which could indicate that poor compressions are the cause. The final stage is to check the injection pump timing before you remove it for overhaul or recalibration. So, in this program, we've discussed the basic operating principles of both the petrol and diesel engines. We've also been through the significant characteristics and basic servicing operations of a direct injection diesel engine. With the MDI, Austin Rover have produced a high-speed diesel engine which incorporates all the efficiency and economy advantages of direct injection. Its excellent drivability, high power output and quiet running will make it a serious contender, not only for fleet and commercial operators, but for every prospective car buyer. A course covering diesel engine philosophy and maintenance has been developed at the Product Training College at Cowley. This will help you gain more knowledge of the operating principles and servicing procedures of diesel as a whole, and especially the MDI engine. The second diesel video program will also cover the MDI engine in more depth. Stop the tape and answer the questions in section 3 of your questionnaire booklet. Fill in the answer sheet, then give it to your training coordinator for return to Austin Rover.